Thank you very much for taking the time today to view our video. Before we begin, we'd like to take a moment to introduce ourselves. There are many aspects to 9.Connects, but it boils down to the fact that we're a PCB-centric organization. We believe and focus on the PCB due to the fact that it is truly the center point of all electronic design. That's where our expertise lies. We provide services not only in the PCB layout, but in design consulting as well. And during the technical portion of this webinar, you will see this expertise in motion. We are now the exclusive North American instructors for Altium Designer. We host 100 trainings throughout the year across North America, and we are excited to bring these trainings closer to you. In addition to our services, we are also a value-added reseller for a number of PCB-related software companies. And just to note, each company has been presented in past webinars. So if you're interested in them, please contact us or check out our website. And by the way, we provide one-on-one coaching for these tools as well. For more information on our services and past webinars, please contact us. Our information is listed in the description below. Thank you for giving us a moment of your time, and please enjoy the presentation.
I don't want to spend a whole lot of time talking about us because I'm pretty sure you're here to talk about DFM. So let's get on to it. You'll notice that when we started this campaign for this webinar, we called it, "Does someone else teach DFM other than the University of Hard Knocks?" We have found that DFM is something that is sorely neglected, and it's something we all learn the hard way through very tedious experiences, maybe due to respins or just the frustration we've had to deal with in having to do a respin or dealing with our program management because of respins. And the question is, well, how do we deal with this? Because the fact is, most of us weren't taught this. If you're an electrical engineer, I know for certain I was never taught layout, and I was certainly never taught anything in terms of manufacturing and assembly. So it's something we've kind of had to learn on the job. And that's what we're trying to do over here today, is give you a good feel, a good introduction to DFM. Some of you may be already experts in it and maybe pick up a nugget here or there of some knowledge. But if you're new to it, hopefully we'll give you a good idea of where to start and where to go from here. What we're going to cover today are two different things. Number one, we're going to talk about stacking up the stack up. What we mean is the layer stack up. It plays an absolutely critical role in your PCB design. It is your infrastructure. And if the infrastructure is weak to begin with, then the rest of it's going to be very, very problematic. The second part is we're going to talk about the DFM gotchas in the layout itself. Okay? So we'll show you a number of different things you want to keep in mind as you're going about, because there's a lot of little things that you can do that can have a profound impact on the cost and time of doing both fabrication and assembly. Let's talk about some webinar housekeeping here first. I have an amazing number of slides, and you're going to see in the next slide that I won't be able to cover all of DFM in 1 hour. As a matter of fact, every time I created a whole section, I had to trim it down. In fact, I probably have about 3 hours of real material. I can't do it in 1 hour, and we promised to finish this in 1 hour because we know that you're very busy. I'm not sure I'll have a whole lot of time for Q&A. So if you have any questions as you're going along, feel free to type that into the question box. My colleague and expert in DFM, Jeff Condit, will be answering those questions, and so you'll get definitely a very good response. Now, if you're asking us something that's pretty extensive, we may have to meet with you separately, but feel free to ask those questions, and he'll get to those as quickly as he can. So one other thing I'll make a statement to is he's actually following the same screen that I am, and he's not going to be able to look at prior slides. So if you do ask a question, do try to provide some detail in the question so that he can answer without having to try to dig back in prior slides, which he won't be able to do in real time. All right, let's get on with it over here. Reading materials. Don't try to reinvent the wheel here. There are standards for a reason. Those standards are because people either been burned by it or they want to make the process more efficient so their job is easier to do. And there's a number of organizations out there, which you can see over here, that deal with standards, right? The ones that we know of on the layout side of things are the IPC and the IEEE. And there are other ones as well, which are certainly good to know if you want to get more acquainted with the fabrication and assembly processes. So just keep in mind that those standards are out there, and procure them for your company because they're very useful to take a look at, and they go into excruciating detail. As I mentioned earlier, I can't cover all this stuff in 1 hour as much as I've wanted to. There's just, every time I run through the slide deck, I keep adding something else to it, which is always a danger. So therefore, seek guidance. Seek your guidance from your contract manufacturer, your fab house, your assembly house. They are more than happy to provide you information up front, because the sooner you get to them, the faster they can get information to you that will avoid issues and always time and money costs when you're doing this. If you have experienced engineers at your company, go ahead and talk to them. They'll tell you their war stories. And if you don't have the first 2 bullet points over here, please do contact us here at 9.Connects. One of our specialties is design for manufacturing. We've worked with customers in the past where they had prototype boards and they needed to get them into manufacturing. We assisted with that. When we do layouts, one of the first things we look for is to make sure that you are actually going to be able to do manufacturing with your boards. And if we see issues with it, we're going to flag that really quickly. Because as far as we're concerned, why do 2 spins? If you can do it right the first time, and you can get through both prototyping and assembly with the same, prototyping and manufacturing with the same boards, then you are, it's going to save a lot of money and effort. All right, I probably should have put this in the prior one. If you're looking for formal training, IPC is definitely one that provides that. They have their CID training, which is pretty well known through the industry. There's also an organization called EPTAC, which actually has taken over a number of the IPC trainings, and by doing that, it allows more IPC trainings throughout at least North America. So they're having more trainings rather than just at IPC conferences. And then they also provide other trainings as well in DFM type of things. So if you're looking for something that's more formal, these are just 2 recommendations. We just know them off the top of our head. We haven't worked with them, but just based on our prior experiences, these are 2 companies that do that. I also want to provide a disclaimer over here, just very quickly. The pictures that you're going to see over here are based on Google searches. Okay? And I just love Google because somebody's posted something out there that we can use, and this is a very visual presentation. There are some slides that don't have stuff on it, and I actually feel bad that I don't have some stuff on it because I just couldn't find a decent picture for it. But in order to get this done in a timely fashion, we do use Google searches. If you see a picture that may be something associated to your company or to yourself, it doesn't mean we're trying to promote or endorse that. We're just simply saying, look, we found this really good example over here. And also we found some examples of things that you don't want to do, so we're not here to belittle any company or any individual as well. So we just want to throw that disclaimer out before we continue along. All right, let's talk about DFX first, because that term gets thrown around along with DFM. DFX is just a nice way of saying design for, well, what? X, meaning X being environment, quality, or cost, or test, or for manufacturing. And each one of these becomes a very big issue all its own. For example, for design for environment, that could be a situation where if you're building for commercial aircraft, you really have to make sure that you're going to be able to handle all the temperature ranges. On a flight that I took to Hawaii a couple of months ago, and I'm sitting there, and they have a monitor in front of us, and I was kind of bored, and I was looking at the stats, which they show on the screen. They're talking about the outside temperature being minus 70 degrees Fahrenheit. And I'm thinking to myself, wow, it's that cold up here, and this thing's going to land in Honolulu, and it's going to sit on a very hot tarmac, which can get up to 100 degrees, and probably even warm in some of the compartments that aren't air conditioned. So, there's an amazing temperature range that some of these electronics have to be able to withstand. So that's an example of design for environment. And I could go through each one of these things as well. I think the key thing you got to keep in mind is I'm primarily going to focus on design for manufacturing over here. And what do we define as defined for manufacturing? We're talking about minimizing the bottlenecks for both fabrication and assembly. And I'll talk more, give a definition of fabrication assembly here in just a moment. But that's where we're going to really focus things here today. And by the way, my background, believe it or not, is actually DFT. That's where I spent most of my career, both in the ASIC world and in the system levels at a defense contractor. So that's just to give you a little history. We've got both DFT and DFM here at 9.Connects. All right, a very brief overview of the PCB design. There's a history of PCBs. What are we trying to do with these PCBs? Well, we're really trying to pack as much in as possible, and that's really been the history of it through the last 90 years. 1925 is when the first quote-unquote PCB concept had been actually developed, and I can go into a whole history, but we won't have enough time for that today. But that's 1925 is considered to be the year in which the first concept of the PCB was actually patented. And then from there, 90 years later, you look at what's come of all of that, from transistors vacuum tubes to transistors to these ICs that have millions of transistors in it. And just to give you one example over here, I thought this was kind of a great example. what you see up here where my cursor is this is a board that worked in a calculator. And this was a calculator from the 1960s. And it had 30 cans on it. So each one of these cans would be a transistor. And you look at the size of this. There's 30 transistors over here compared to this one chip, which probably has over 1 million transistors in it. So you're seeing that you're packing more into the components, especially the ICs. You're trying to get as much transistors in there as possible because that's ultimately the logic that you're trying to drive. You're also shrinking all the passes. It's amazing. You look at one of these resistors on this board over here, and then 0402, you could probably put 4 0402s in the same place that you have one of these plated through resistors. And then, of course, there's an increased component density on the boards because of the fact that we can do blind and buried vias, that we can put these components very tightly packed to each other. Even the component packaging is becoming amazingly tight as well. So that's what we're dealing with over here. So as a result, all this is driven by the overall speed of the product. Everybody wants their product to respond instantaneously, right? We don't like to wait 3 or 4 seconds for a response from our computers or our tablets. We want increased functionality of the product. So remember, many years ago, everybody was just jazzed to have a remote control that would just turn on and off the television set and change the channel and maybe change the volume. And now you look at these remote controls and they can do almost everything except brew coffee. It's just amazing amount of functionality that we put on our products. We have a high expectation of it. Another example that I was thinking about the other day is that when I was a kid growing up, you would buy a dedicated handheld game. I remember the biggest one was called Space Invaders, but that's all it did was Space Invaders. Now we think of that and think, that's boring. We want something we can stick a cartridge in, or we want something that we can download an app into, and so when we're done with the game, we can move on to another game on the same platform. So we have a huge expectation of our functionality. That means we have to also decrease our cost to manufacture and assemble, and we've got to decrease the time to manufacture and assemble. And a lot of things that used to be done by hand just aren't acceptable anymore. They've got to be done by automated equipment, and that's really what DFM is how do we work with the equipment that's going to turn theory into reality. All right, before we go any further, the recommendations I am going to show today are here to reduce costs and time. And none of these recommendations are absolute. I know there are people who are seniors and experts in this who are probably sitting in this today. And I'm going to show a lot of slides, and you're going to say, well, there's a way to work around that, or I know a better way of doing it. There's no doubt about that. So we just want to say that what we're showing is not the end-all and be-all. There are ways to work around things. Just keep in mind that when you do work around stuff that is not common or it creates a bottleneck in the fabrication or assembly processes, you're going to add more cost and you're going to add more time. But what I generally find with both the fab houses and the assembly houses is that they are more than happy to try to work with you to make it happen. They enjoy the challenges, but there will be a cost and time associated with it. Okay. I want to talk about terminology for a moment because I think there is a little bit of overuse and abuse of different terms, and I want to make sure we all understand that we're on the same page. One of the terms that's been coming out quite frequently now is this thing called a contract manufacturer, as opposed to just talking about a fab house or assembly house. And a contract manufacturer is what I call a broker. It is someone who distributes the work to the optimal board house or to the optimal assembly house. All right? And they may have these things in-house, like an in-house fabrication, or they may have an assembly operation. They may have both, which is kind of rare here in the United States. Or in some cases, they may have neither. They may just say, look, we know who to send this out to. Just give it to us, and we'll handle the rest. And you'll see why there's an advantage to that in just a moment. The other thing is to procure components, and that can be a very difficult thing. If someone's going to be able to procure components to you, there's a benefit to that. So that's what a contract manufacturer brings to the table. You're talking to someone who can broker this stuff out. A fabrication house is a house that basically fabricates the boards. And I'll talk a little bit more about different types of fab houses in just a moment. But just keep in mind that you'll hear the term fab house or board house or fabrication house. They're all the same thing. And then you have an assembly house, and what they are there to do is basically to assemble things. You're supposed to populate the boards with components. The soldering, the through-hole, the SMA type of stuff that you've heard of, that's all handled by them. And just, by the way, it's just generally abbreviated as ASY or ASSY. So in any of my slides, if you see that, I'm referring to assembly. And that's usually the abbreviations I've seen in the industry. All right, terminology continued. Here's something that always brings up a little controversy, and I'm just going to try to keep this to its simplest level. There are things called PWAs, PWBs, and PCBs. And if you work in a company that's very formal, and definitely if you work in defense, you'll know that you've seen PWBs and PWAs. And what are they? Well, PWAs are printed wiring assemblies. And actually, let me jump over here first. I always put A first, B second. I don't know why I've got that switched in my mind. But the fact of the matter is, let's talk about PWBs first, because that's a printed wiring board, or basically a bare board, and which is what you see over here in this picture that I found, as opposed to a PWA, which is a printed wiring assembly, which is a populated board. So you can see this example I found out over here. This term PCB is a very, very generic term, and though it generally refers to a bare board, it certainly can also reference a populated board too. I'm just going to call things PCB today because you'll already hear enough terminology, and to throw PWB and PWA into the mix is not only a tongue twister for me, it's just going to add more vocabulary and some confusion to this. So for my purposes, I'm going to keep to the term PCB. All right, fabrication houses. What we've noticed with fabrication houses is that they tend to have differentiation, because they're not all the same. So they try to do things that have a specific focus so they can differentiate. For example, there are fast turn time ones, meaning that if whatever you send them, they'll build. You just have to know what you're doing. For example, PCB 123. They can turn these things very, very fast. They do have a very specific set of parameters you've got to follow. But whatever you send them, and as long as you're within those parameters, that's exactly what they're going to build. There's not going to be any QA on this. It's not going to look for anything. They're just going to assume that you know their processes, and they're going to turn a board for you. Okay, so very inexpensive, very quickly, but you got to know what you're doing. Then on the opposite end, the extreme, you've got what's called high reliability, which is extremely pricey but very necessary for what you call Class 3 builds. And I'll talk about the classes in a minute. But basically, if you're doing military, or you're doing aircraft, or you're doing anything that could, if it fails, could end in the loss of life, then this is where you want to go. You want to go with high reliability. You don't want this thing to fail. There's also high volume. So if you've got that, if you're building circuit boards for a little trinket that's going to go into a Happy Meal box at McDonald's, and you're supposed to make 20 million of these things, then you want to go with a source that can just pump these things out as fast as they can. So they're geared for high throughput, and they're going to expect that you're going to work to their equipment so that there's no bottlenecks in that effort. And then you also have what we'll call the general ones, the jack of all trades. They're useful for low production, for prototypings, and everything in between if you're not looking for anything very specific, which I've mentioned up here. So those are the different types of fabrication houses that do exist. All right, let's talk about material considerations now. Let's talk about the stack-up. The key thing that I want to mention about the stack-up is you've got to let the contract manufacturer do their job, or your fab house do their job. Okay, if you're going to try to do the stack-up on your own, then you really want to work closely with them to understand what's going on. You have to understand their processes, and you have to have some experience in it. Okay, so I know there are tools out there that you can pick up, and they'll help you do layer stack-ups, and you can go pick materials all day long with it. That doesn't mean that they can manufacture that. And if you wait to the end and throw that at the fabrication or the CM, they may come back and say, sure, that $1,000 board is now $20,000, and they're saying, sorry, we cannot build this. This will not work through X number of our processes, and we just can't build it. And as a result, you're going to have to start again. And that's why the stack-up becomes so important. Now, in the past, most people relied on a material called FR4, and everybody, it was such a common denominator that you really didn't have to worry about this stuff. But with high-speed design, with RF, with microwave, these exotic materials have advantages and disadvantages. And since most of these fab houses tend to be primarily geared for FR4, these advantages or disadvantages, especially with temperature coefficients, or the softness of it, or their flexibility, or their hardness, or their brittle, have a huge impact on their ability to get it either through fabrication or assembly, which I'm kind of jumping down over here. But one of the things, for example, when you're doing high speed, is a lot of people want something that's got a better dielectric constant than FR4. And but you got to keep in mind, for example, that dielectric constants are actually impacted by moisture and temperature. So if you happen to be building some piece of equipment that's going to be sent out on seas, high seas, and you know there's going to be moisture all around you, then you're going to have to compensate for that because your dielectric constant may go up because of the moisture in the air, or if the temperature is always hot because this device is going to be sitting on a fishing boat in Hawaii, right, where the temperature is going to be very warm, or a combination of both. There's also thermal expansion issues here. For fabrication, you have what's called registration issues. So one thing to keep in mind with fabrication is that they do these things in what they call core, and core has a foil on the top and on the bottom. And if you ask, for example, like for a 4-layer board, well, that means you'll have 2 pieces of core with the copper on the top and the bottom. You'll etch those copper pieces depending on based on what you put for the layers, and then they're going to laminate those things together. Well, during that lamination process, you have something that's called registration. And so this stuff gets all kind of mushy and gushy. It's not all rigid. And those registration issues, because of the thermal expansions over here, can become very problematic. So that's why it's really important to let your CM or your fabricator know the size of your board and the materials that you're seeking, because they need to make sure that they can even register it. The other thing, too, is that with assembly, with surface mount parts, they can pop off. So if you've got like a resistor or a chip capacitor, and that board is flexing because of the materials that you use, it can actually pop it off. So that's another reason why you want to be very aware of the thermal expansion. And of course, lastly, the environment in which it's going to reside. That, even though it made it through fabrication assembly, are you going to now have a quality issue later on because it can't survive in the environment in which it's trying to operate? The other thing you want to keep in mind, too, is you want to talk to your contract manufacturer or your fabricator about size, shape, and thickness of the board. There's issues with warping, and that's what you're seeing over here, is that this board actually warped. This example that we found. We'll talk about one way to minimize warping, because some of it has to do with material, some of it has to do with how you spread out your copper. And then again, it goes back to registration difficulties as well. The bigger the board it is, the more difficult it is to register it. Okay, talked about classes, or I mentioned it very briefly. Let's talk about classes for a minute. There are 3 classes. These are in the IPC. If you ever take the CID training, you'll get very familiar with these. But the idea here is that most fab houses want to know the class that you want to operate in, and there are 3 classes. The commercial one is basically our consumer products. And the way I kind of look at them is in terms of their criticality. And so yes, we may be in tears if our television doesn't work, or if our laptop decides to quit on us, or our iPhone drops to the ground. It's very inconvenient, but it's not life-threatening. And so a lot of stuff you might be able to get away with is class 1. Whereas an industrial class over here is something that a downtime will actually have some significant impact, primarily a monetary impact, like ATM machines, business servers, factory equipment. If those things go down, you're going to lose a lot of money because of the fact that you can't conduct business. And of course, there's class 3, which is high reliability. And if it fails, it's going to result in a death, right? You want your aircraft to be built with class 3 military operations, or equipment for our military operations. They want to be class 3. They can't have that stuff fail while they're doing an operation. Medical, life-saving equipment, it's got to work when you turn it on. And when you turn it on, you expect it to constantly work and that there's not going to be any issues with it. So one of the things that one of the CMs recently told me is that they really appreciate it when someone tells them which class they want you to build this on. All right, another aspect of this that we don't really think about, but it's one you want to consider up front, is your ability to do holes. Okay, because we want to do via holes for the most part, because we want to go from one layer to another. That's a major capability of our ability to put printed circuit boards together today. So we may not be doing a lot of through-hole stuff, but vias are definitely important. There is a general rule of thumb, which is that the thickness of the board dictates the size of the hole, of the size of the hole of the via. Okay, and so if you have a board that's let's say an 8-to-1 ratio, so the thickness of the board, you can go with an 8-to-1 ratio, and for high reliability boards, that's going to be the max that you can do. But for almost any board, that would be fine, even for 10-to-1 for typical boards. And some houses can even go 12-to-1 or greater, but you will have some concerns for your reliability. So keep in mind, what are you doing with the via? You are basically drilling the hole through this thing, and then you're plating this hole. So the thicker the board is, the more difficult it's going to be for you to get the plating all the way through. And so that's why they give this general rule of thumb, or these ratios over here. So for example, if you have a 100 mil board thickness, then a 10 mil hole is the minimal size. Okay? And we'll talk a little bit more about this as we go along. So just keep that in mind here. So continuing with the holes, there's these things called blind and buried vias. And the biggest problem that I see with this, especially in Altium Designer, and that's where I come from, is from Altium. We're trying to keep this tool agnostic, by the way, and I think most tools can do the same thing. But when I'm talking specific to Altium over here, is that you can create blind and buried vias all day long with Altium. That doesn't mean it can be manufactured. And just for everybody's reference here, number 3 represents a typical through hole. That means it's going to go all the way through the top, from the top all the way through the bottom. There's also what they call a buried via, which starts at one of either the top or the bottom, but it ends somewhere in the middle. And this is a good example here. And then number 2, you have what's called a buried via. Pardon me, this is a blind via up here. Number 1 is a blind via. This is a buried via, meaning it never sees the light of day. It's always in between the layers over here. So the concern that you always have is creating a blind or buried via in such a way you can't manufacture. And you may say, well, how is that? Well, you have to, again, understand the manufacturing process. And here's a good example of it. So this is a 6-layer board here. And if you're calling out for a 6-layer board, what you're doing is you're saying, look, take 3 cores with material on it, which basically is copper. It has copper on the top, copper on the bottom, and a certain core material. It's FR, it could be FR4, and basically etch out the top, etch out the second layer that's on the bottom. Okay, so you take this individual board, you would etch these things out, and then after that, if you did have, for example, a via that was going from layer 1 to layer 2, they would actually drill at that point in time, and then they would plate it. Okay, and then they would do the same thing for this middle one for 3 and 4, and then you do the same thing for 4 and 5. And then after they are done with these things, then they actually put this material called pre-preg, which is really a sticky glue, and they laminate these things together. And if there's a through hole, then at that point they'll drill it through and then they'll plate it. So keep in mind that there's also a major cost with this, because if you got to keep stopping the process to do these things, it takes longer to do and it's more intricate. The thing that I want to mention over here is that, for example, if you decided that you wanted a, let's say, a blind via from layer 2 all the way down to layer 4 over here, you're going to cause a tremendous number of problems. Most board houses would not be able to do that because you're asking this thing to end here. So now you're saying to end at this copper, go through this pre-preg, start on this copper, go through this core, and then on this one. It just doesn't work very well that way. So if you understand how they're doing these things, then you can set up your blind and buried vias in such a way that you don't cause an issue with manufacturing. Because the problem that you'll see with this is that if you didn't do this right and you hand it off to the fabricator and you have a very dense board, and they say we can't fabricate this thing, or it's going to cost $20,000 to fabricate a board that should only cost $1,000, well, then you're probably going to have to make a difficult choice of spending the $20,000, or more than likely, because you're trying to get this out as a product, you're going to have to go and redesign the whole thing again. Okay? So just be very aware of blind and buried vias. Understand that they do cost money, and you've got to set them up correctly. All right, stack up holes, or pardon me, stack up the holes here. So it's kind of interesting that when we call out for something in our PCB layout tools, and it doesn't matter what tool it is, we can kind of add numbers as we see fit. So, but in reality over here, the drill sizes actually come in increments of 2 mils. So they don't step them up in 1 mil. They actually step them up in 2 mils or 0.05 millimeters. The one thing to note is that when you place one of those vias or through-hole pads on your board, you're talking about a finished hole. So let's say, for instance, you call out for a 7 mil hole. That's a finished hole. So what your manufacturer is going to do is they're going to say, all right, he needs a 7, or he or she needs a 7 mil hole. We're going to drill this out to 10 mils because we're going to have to plate this thing over here, and we want to leave enough space. So they may actually drill it out to 10 and then plate it, and then maybe make enough plating so that there could possibly be 2 mils of copper on it, depending on the number of copper ounces. But just keep that in mind that that's how they're going to work that. It's not an exact process, because when you're adding copper or you're removing copper, you're doing an etch, and it's a chemical process, and that can't always be, it can be controlled to a high degree, but not to a perfect degree. We'll talk a little bit about that as we go along. So rules. Based on information that you get from your manufacturer or your CM and your assembler, you can set up your trace rules, especially if you're doing high-speed design, your trace width and your trace spacing. If you're doing anything that has to do with impedances, that information will come from the fabricator, because they're the ones who will know the trace. They have to provide that to you. If you're familiar with the impedance equation, pretty much the 4 factors, which is the height of the copper, the distance from the copper to the plane, the dielectric constant, and the width of the copper has a huge role in that. I probably should have left the equation up there. So those 4 factors are all controlled by the stack up, and so that's why you don't want to just go into the width rule of a rule checker and just come up one out of the blue. You really want to get that from your configuration manager or from your fabricator. Clearances will play a big role in that as well. Component clearances are definitely key, especially for the assembly side of things. They're going to want to know how their machinery is going to work. How are they going to place things in it? Because you obviously don't want, they're all using pick-and-place machines. You don't want them to do it by tweezers. It's going to take too long. But that equipment has to have enough space to drop those things in, or it has to have an order of operations so it doesn't smack into something larger. Then maybe they'll put down the smaller stuff first and they'll put the larger things down later. Some of those things may actually have to be put in manually or by hand, depending on how you set the board up. So again, when you're doing design for manufacturing, you're thinking about those things ahead of time so that you're not adding cost because of the fact that they've got to do a workaround there. And of course, the hole sizes, which we talked about as well. All right, let's talk about the PCB board size itself. The thing to keep in mind here is, again, that the fabricators have their ways of doing things. And one of the things that they do is that when you call out for a board, they're going to use a default size because this is the stuff that's going to run through their machine. Now, the example I provide over here is not the only standard size. It's one of the most common sizes. So by default, when you call out those layers, they're going to pull out core material that is generally 18 by 24 inches. Now, can they do things that are bigger? Some companies can do it, okay? But it's, again, more money and it's more time. But they're going to try to fit stuff in that works the best with their equipment, okay? And it's important that it fits within this over here, because if it doesn't, then they're going to have to start doing things like special tooling over here, and that does cost additional time and money. And of course, you need that tooling over here because, again, most of this stuff is automated. So you can see in this example over here, this board is pretty large, and they were able to at least grab the edges here. So they made sure that there weren't components on the edges, so it could grab this and run this through. This is for a wave machine. Or here's one that's routing about, and you can see the tooling equipment over here holding on to this while it's being milled out. So you want to make sure that you have those things in mind. For fabrication assembly, they may need as much as 2 inches around the edge. So if you're thinking, oh, well, I want to get the maximum usage out of this board, so I want an 18 by 24 inch board, you're going to make it very difficult for them because they do want to have tooling that can basically grab the side of those boards. So just bear that in mind if you decide that you want to maximize out the board space. Related to that is the concept of panelization. So now that you know that most boards come in an 18 by 24 inch size, you're saying, well, look, if they're going to use that material, I don't want to just have them do one board on this. I want them to do multiple boards. Well, they don't want to waste the material either, right, because that material costs them money. So if you do ask for an X number of boards, probably by default they're going to panelize this because that's going to be the most efficient way. And you certainly can ask them to do it as well. The big thing I find with CMs, and I talk to them quite often, is they don't want you to do the panelization for them. Just tell them what you want, and they'll be more than happy to do the panelization for you. Because when you start doing it, you're now saying that you know the equipment better than they do, and more often than not, there's things that you don't know about, especially if you don't have experience with it. Now, if you have your own in-house stuff, then yeah, you'll probably have to get involved with it, but most companies are handing this stuff off to those who know what they're doing here, that it's an outside operation. Just tell them that you want it, and they'll be more than happy to do it. They don't want to waste materials. Okay? One thing that I'll mention over here as well is that now here's an example. First and foremost, you can see they duplicated the same board 6 times, which is obviously a good efficiency over here. You can also have different things put in here too. So say, for instance, you have a product that has 3 different boards and they happen to fit within the 18 by 24 area. You can certainly do that, but the catch to that is that all boards must have the same stack up. I don't want to beat up on anybody. We worked with a company a couple of months ago, and they had us do a board, I think it was 6 layers, and then they gave us the other board, and they had every intention of panelizing it. However, they wanted the new board to be 8 layers. We said, well, wait a minute, we can't panelize this because the layers aren't matching up. And so it became very problematic. But so if you're going to do this, you really have got to think this out. And the key thing is that the stack up is uniform across all the boards that are going to be panelized if they're going to be different. Okay, let's talk about routing. What I mean by routing is not copper routing, but milling out of things. So a router bit is cylindrical, okay? Even if it may be square in a rest position, when you spin it is cylindrical. And that means that you cannot expect sharp corners or sharp inside corners. Now, this board that I found over here did a pretty slick job of it here. But I'm pretty sure if you zoom in over here, you'll probably find that there is a rounded edge. Now, if you're using a laser, that may be a different thing altogether. But just keep in mind, if you're trying to have something fit exactly in there, you're not necessarily going to get a perfect edge. You may actually have to over-mill it so that you have so that's removed out so you can get the equivalent of a sharper edge. Okay? similar to this is the concept of a slot. So a lot of times you've got to put a slot into something, especially for some type of connector. If you're going to do a slot, just make sure you don't make it too narrow. So again, go back to your fabricator, your CM, ask for their abilities to do it. The general rule of thumb that we have found is that the slot size is limited to half the board thickness. So for example, if you have a 50 mil thick board, the slot should be at least 25 mils or larger. And that kind of makes sense if you think about it. In extreme here, let's say for instance you had a 1-inch board, which it's really difficult to make, but let's decide you wanted to have a 10 mil slot in there. Can you imagine a 10 mil bit trying to go through a 1-inch board? I mean, it wouldn't have enough material on it to make a lot of effort on that. It may do it, but it would be a very slow and tedious process. So work with your fabricators on this. All right, let's talk about fiducials. Fiducials are really important creatures, and they get left off of boards quite often. I know one particular CM, every time he's given a presentation, he makes it very clear that if you bring a board to him, he will make you fit fiducials on his boards. They are very, very important. They are for basically helping the registration of the board, especially during assembly time. So what are they? They're basically a little copper round pad, and they can be 1 millimeter up to 3 millimeters max. And there's very specific requirements to this, by the way. And then in terms of its clearance, you don't want to have any copper around it. So here's a really good example over here of a copper pad. Over here, it's probably been covered by some type of finishing material, and then they remove the copper around this area here. And you notice that there's 2 of them on this particular one. It's a really great example that someone has out there. It does require 2 fiducials. 3 of them are preferred, and then you can see here are the requirements if you do this. One additional thing over here, well, there's 2 additional thoughts. If you do have a fine pitch component, something that's got like 1,000 VGA ball grid arrays on it, then you want to, or ball grid, pardon me, an array of ball grid. If you have something that's got 1,000 ball grids on it, you may also want to add fiducials very close by to that to make sure that the placement of that component is as dead on as possible. Also, the other thing I'll mention here, I didn't put a note in here. I think I did. Here it is. No anomalies. When you do this over here, sometimes you can see through this material, and what you don't want to do is have copper lines running near it or underneath it on different layers, because that can actually throw off the optical equipment. So just keep that in mind as well. Okay, let's talk about tooling holes for a moment. So 3 pins for the purposes of holding and aligning the boards, and they're definitely used in fabrication for registration, and in some cases the assembly houses can take advantage of that as well, depending on what the assembly house, how they get the board, whether it's all still in one panel or if it's already been broken out. In some cases you've got to break them out. It depends on the situation and the components that you're placing on it. But if you're going to work on the CM to do it, make sure that you're dealing with the optimal placement. Where do they need these things? What is the hole size? And most importantly, don't plate it. Okay, because the problem again with plating is that you can't really control the amount of copper going through that hole, and it's going to throw off the tolerances. You'll get a better tolerance just by simply drilling it through than to try to plate it afterwards. The benefits to this obviously is going to be a faster processing time through fabrication assembly, so it's less tooling that they've got to do to get the equipment up and ready to run your boards. And of course there may be possible cost savings to that because you save them some time. Copper weight. Copper weight's an interesting creature. I always thought it was a weird thing that they called copper weight, because to me it was really a copper height, and that's really what it is. But the reason it came about as copper weight is because it's derived by 1 ounce of copper being rolled out to 1 square foot. So that's what they mean by copper weight. Now over here I say ½ ounce of copper is common. Up to 2 ounces of copper is also common as well. If you want to, really, why do you want that? Well, it's because you desire more copper, either because you need more electrical connectivity, you're dealing with basically high power, or you're dealing with thermal connectivity, your components are really putting a lot of heat out and you want to draw that away. So that's why you want to have more copper here. And more copper is needed for thicker plated holes. Okay, that's the other reason that you do this as well. The disadvantage that you have with this is that you can easily ask for more copper, and there's a lot of different ways to ask for this. You could have different levels of copper on, let's say, the inside versus the outside of your layer stack here. The key thing to keep in mind is that the more copper you ask for, it's going to impact your trace and space. So if you're trying to put things into a dense area, but you're putting a lot more copper in there, you're going to have more trace space, and you're going to have more spacing between the traces. Your width of your trace is going to be larger, and your spacing between the traces is going to be large as well. This is a really good example over here of what happens during the etching process. So a lot of people don't realize that the vast majority, though they are working on what they call additive processes, I'd say 99%, if not more, of the processes currently going on today is that you have a substrate with copper on it, okay, and what you're doing is you're etching away that copper with some type of solution. So in order to leave the copper that we want, initially you do something called an etch resist. You put a material over that area that you don't want to have etched away. Well, then you dump this into the bath over there, and it certainly etches this stuff away, but keep in mind that that chemical is also going to get underneath here, and you're going to get a trapezoidal effect. And of course, if you have more copper, the more impact that you're going to have over here with your trace. And by the way, even though this looks trapezoidal this way, that trapezoid could be flipped, where that where the acid's making actually more inroads next to the substrate than it is with the edge resist. So the fact of the matter is that when it comes to traces, it's not an exact process, right? You're dealing again with chemicals, and also how quickly the chemicals are being combining with the copper, by the way, and we'll talk a little bit more about this in a moment when it comes to spreading out the copper evenly. But it's not a super exact science. There's they try to get this down as much as they can, but you're never going to get a square piece of trace over here. And if you were with me with the last webinar that I was talking about with high-speed design, that becomes very problematic if you're trying to get your impedances down to an exact science, or if you're just trying to make sure you don't have certain frequencies that may turn your copper wire into actually an antenna because of this situation right over here. All right, let me talk about silks for a couple of minutes. Silks are interesting, and I'm going to kind of throw something at you here in just a moment that's going to really surprise you. What are the purposes of silk, first and foremost? Well, obviously, a company logo, something to be proud of, right? And of course, if you have certain markings that you got to put on there, if it's UL, then hey, you want to put down you got your UL qualifications. If it's been CE certified, you want to put that on there too. Things like serial, rev, documentation numbers, extremely useful, especially when you're trying to move your product through things. Okay. What other purposes? Polarities. Polarities are really important, especially if you're going to be doing hand soldering, because you want to make sure things are put in the right way. Though this information generally can be handled through the pick-and-place files themselves. But if you're going to be doing anything with testing, for example, test debug, or if you're going to be doing anything by putting stuff in by hand, polarities are definitely going to be important. And the other thing, too, is that if the board is being exposed as a part of the packaging, and I found this really cool board over here, that, of course, you want to make sure the silks are there so that it provides eye candy or good information so that the people can enjoy it. So I guess the shocker that I'm going to put to you here is that from a DFM point of view, silk is actually a detriment. Okay, and it really becomes a detriment when it comes to designators. And there's more reasons not to put silk on a board that's going through its final manufacturing processes than to put it on there. Number one, it does take up a tremendous amount of real estate. Wherever you're putting that silk is a place you're not putting your component. So on a very dense board, it doesn't make sense to have silk there because do you want the component and its functionality, or you want to be able to read it? Well, with the tools that they have these days, you can probably read it on another layer. So there's no reason to actually waste the real estate that you have on your board. It adds a process to fabrication. If you can remove that altogether, if you're removing a whole step out of the fabrication process. And it only serves as really a test or a rework function. Why do we put this stuff over here? Well, I know that there's an artistic level of doing a print circuit board design. And adding that stuff in there makes it look really cool. And there's some really amazing silks that I found when I was looking for this picture. But the fact of the matter is that really, unless it's a test or a rework function, who's really going to see this artistic work? And that's kind of the tragedy of it, is that we stick it into a container, and most of the time it'll never see the light of day unless someone breaks it open or they have the ability to repair it. Okay? So it only really serves for a test or rework function. It also provides hints for those who are trying to reverse engineer your board, and that's really a big problem. When these boards go overseas, there are people who take these boards and say, this is a pretty cool board, let's reverse engineer it. Well, if you tell them that it's an R7, you've already given them a hint that's a resistor, right? And they can look at the components and do those things, but the more information you're providing over here, the more information that they can look up or try to find to see if they can reverse engineer it faster. Will they reverse engineer it? Yes, if there is a will or there is a way. Don't give them any more hints than necessary, right? So, and a manufactured board, why even bother putting it on there? Because again, no one's going to see the light of day. Don't give someone that advantage. The last one that we're going to mention here too is it does compromise the ability to clean underneath the components. Now this one that I happened to find over here, I'm not beating up on this individual, but it was really interesting because we had a very similar issue with another board that we were working on for high reliability. It's a medical piece of equipment, and there was some silk underneath. And this actually becomes very problematic when you put silk over here. And the question is, well, why? Well, because you'll put the solder paste on here, because you use solder paste when you're doing SMA parts, okay? And you do the solder paste here, and then you place the part down, and then afterwards it will go through a wash or a bath. Well, the problem is that these are acting as barriers because there is some height to it, and as a result, that material cannot be properly cleaned out. And so it may work just fine now, but you may have left an acid, or you left some material over here that later on could cause a corrosion and a fail. That's why it could be a possible high reliability issue. All right, let me talk about component placements for a moment. Wow, the time is moving here, so I may have to push a little bit faster here. Our key thing here at 9.Connects is we won't start the routing until the component placement is done. And we always recommend, and we always have the design team review it before we always start, because once you start the routing, you start moving things, you got to tear up the routing. The key thing to understand with this particular slide is your part running hot? Or let me take a step back. Understand your components in general. Does the part run hot? Is it noisy, or is it being impacted by noise? Is there a mechanical aspect to it? So if it's a connector with a latch, are you going to have enough space for that latch so that you can open it? Can you get your fingers in there so you can open the latch? These are the things that have to be considered when you're doing these parts. Is rework going to be an option? So you want to make sure that you don't pile on a ton of resistors and capacitors in the same vicinity as a BGA, where you may want to replace that BGA. If you're dealing with mechanical housings, you want to make sure you got the height clearances. Specific placement for connectors and LEDs. Well, why do you put an LED or connector on there? More than likely because you want it to communicate with the outside world. So the placements definitely need to be understood. Orientation can play a role, especially in the type of soldering methods that they're going to use in your assembly. So make sure you do ask them what type of materials they're going to use, or what type of machines they're going to use, because the orientation can play a key role in this. For the connectors themselves, if you're going to put connectors on there, the optimal situation is to put them on parallel sides. Here's a good example of it. So you can see these overhanging on this side, and they're hanging on this side. If you put them adjacent to each other, still can be done, but then they can only populate so much of it through their pick and place machines, and the rest of it's going to have to be done by hand, which obviously adds more money to the process. Direct wire placement. Direct wire placement over here. This is a homemade thing, so I'm not here to beat up on anybody in particular, but this is something you definitely want to avoid in DFM. Okay, using wires directly, there's certainly an advantage. You don't have to pay for the connector. Okay. The problem with this over here is, well, there's twofold with this one. Number one, they use a surface mount area to wire these things on. So all you're doing is assuming is that pad itself is holding this back. Plus, there is a massive amount of strain that's always put just on the edge here, where the wire is coming off of the PCB board. Okay? And even if this was going through a through hole, you still put a lot of stress right here where my cursor is. So what do you need to do? You need to drill 2 holes. One of them so you can feed the wire through it, and the second hole to loop it around and then solder it in. And that will provide a lot of basically strain relief. The other thing you can always do is you can run these wires parallel. So you run the board, you create the board out a little bit longer. You run these things off parallel to the board, and then you put a clamp on that and let the clamp take the strain. All right, thermal reliefs. Thermal reliefs are something that you really use for through-hole pins. So a lot of people don't realize that, but they're for through-hole. You don't really need to use them from SMA, and the reason you don't need to use them from SMA is because of the soldering process for SMA. You usually heat the entire board up evenly, so the heat is going to stay. It's not going to be pulled away, unlike when you're doing a through-hole part where you're concentrating the heat in one local area. So if you have a through-hole, let's say a resistor, and it's attached to the ground, and you have a massive ground plane in there, that becomes problematic because that solder, or the heat that you're trying to get from the solder gun, is just going to be pulled away from by the entire plane. So what you can do to kind of reduce that escape is to basically put these thermal spokes on there. Okay? And by doing this, now you can solder a ground, let's say a through-hole resistor pin that's going to go to ground without too much of an effort here. Okay? Copper considerations, two big things here that I want you to recognize, and this one comes from a real board, so I'm really surprised that they didn't have some issues with it. This over here is copper slivers. So if you were to put a whole field of these things together, and this is going through one of the layers that was actually a plane, this is going to be very problematic because you can see how small these are. So either they're going to be etched away entirely, or worse, they may actually break off or they can lift off. Because remember, it's just a foil on top of a laminate. So this is kind of a dangerous practice to be doing here. You really want to leave some space there so that that copper is going to remain, or better yet, just remove the copper altogether in this area because it didn't really provide much of a benefit to it. This one over here, I exaggerated this one a little bit, but I did this to emphasize the point. Here's something that's all ground. But if you look at this leg over here, there's only 3 tiny slivered areas that will provide that ground. So you want to make sure that you have adequate copper going to all of these things. The biggest problem I find, Altium definitely is one of those things. If you tell it to pour a polygon, it's going to pour the polygon. But you've got to look at what you got poured because you have to adjust the properties and the design rules to ensure that it poured properly. Okay. Fill patterns. Here's an example of a board, very good one we found here on the internet. The problem with this board over here is the fact that there's not enough copper in this area here as opposed to copper in this area here. There's 2 problems with this. First and foremost, if you have a layer that doesn't have much copper to it and you have a ground plane on another layer, you will get warpage, guaranteed. Why is that? Because of the copper coefficient expansion is not equal to the laminate, right? So the laminate is things that take the copper, the core of one and the core of the other, and they mush them together. Remember, there's copper on top of that. And when you heat these things up, because heat is definitely a part of the fabrication process, the copper is going to expand differently than the other materials, and as a result, you're going to get a warpage. The other problem that you have with this one here as well, even if this was just a 2-layer board and you weren't doing any type of lamination, the problem that you got here is that when this gets put into the solution, the chemical depletion rate is going to be different in these areas over here, whereas over here you're trying to preserve the copper, okay? So there's not as much deterioration of the chemical over here as opposed to this area here where there's a ton of deterioration going on, or it's actually vice versa, well, because you're trying to remove all this copper here. The point I'm trying to make is that the chemical depletion rate over here is going to be very different across this board, so you'll have an uneven trace. You may have uneven traces, or you may have uneven pads when you do this here. So what's the solution to this? Well, you can add these fills. You can do a crosshatch over here. You can even do a polygon pour over here as well. And that will definitely assist here in making sure that the chemical depletion across the entire board is equal. Now, yes, it may impact EMI or may impact something else in impedance, so you've got to balance those things out. But from a manufacturing point of view, adding these in here is a huge benefit. Solder mask. Solder mask is an interesting creature because I think we confuse solder mask and solder paste as to what they are trying to do. A solder mask is a fabrication process opposed to solder paste, which is an assembly process. Okay, so that's the first thing. And what is the solder mask trying to do? It's really trying to prevent the copper from being exposed in the environment after the board has been released. Okay, because copper, when it reacts with the oxygen in the air, it actually changes over time, right? And that impacts its connectivity. So the solder mask prevents that from happening. It also acts as somewhat of a dam. So if you look at this, this is what they call a dog bone, and you have a pad over here which the BGA ball grid would sit on, and then you have this little piece of trace, and it goes into a via hole so that it can be dispersed through other layers. So this is how you do what they call a breakout. So this solder mask over here is preventing that solder from basically going into this hole and getting wicked away, right? Because the solder is already the ball itself, and if you didn't have this over here and you melted this, all the solder just drained right down this hole over here, and you're really up the creek. It wouldn't attach at that point in time. The key things you got to keep in mind with this over here is you want to make sure you leave enough distance between these two. If this is really thin, that could break off, or a piece of it can actually embed itself right on top of the pad. And of course, what's its purpose is to prevent soldering from happening, so you can actually compromise the solder at that point in time. Okay. Let's talk about solder paste. This is an assembly process. What is solder paste? It's basically paste plus solder. Okay, it's a mixture of the two. In the past, you used to squeegee these on to a board, or you basically had this this metal sheet that would go over your printed circuit board. You'd squeegee it over, and then you remove this this metal plate. Now they have printing methods which provides far more accuracy. The one recommendation that we will make with this stuff over here is that, and most of the tools will allow you to do this, but for the solder paste, make the solder paste hole slightly smaller than the landing itself or the copper itself. And the reason why I do that, especially with fine pitch parts, is that obviously this paste over here can somehow flake or break off prior to it being heated. Now, in most situations, if it's overhanging the solder mask, it will suck itself back onto the pad itself and won't be an issue. But if it gets far enough way off there, it could roll off and it could impact something else. So the recommendation we make on that is, hey, keep this stuff as try to make that pad, the solder paste pad, is a little bit smaller than the landing pad of the copper. Annular ring considerations. Okay, so people always ask questions about when do you use teardrops, and teardrops are really kind of a quick fix for a larger issue. Here's the issue that you come across. Obviously, you want to use a V-up, so you've got a trace that goes into a annular ring, which is basically the copper around the hole that you've got, the plated hole. Now, in an optimal situation, it will look like this very first picture that I'm circling with my cursor. But unfortunately, let's face it, there are two issues here. You've got tolerances with the drill hitting dead on center, so that the drill may not hit dead center. And number two, it may come in at an angle. So even though it looks good on the top, at the bottom it may have already angled off and caused an impact. And where my cursor is over here, this cut where the between where the trace is and where the pad is going to be become a problem. And in fact, in Class 3 components, this is not acceptable. Okay, they call this a breakout. The lower classes will allow this, but there's a certain percentage you still have to maintain between the trace and the pad. So how do you get around this? Well, first and foremost, talk to your CM, and then recognize their tolerances. And when you build these vias, build the tolerances into those vias. If they say, look, we can handle a 10 mil hole, but you know that there's a 4 mil tolerance issue, then make the thing 14 mils. Make them bigger to begin with so you don't have the problem to begin with. The other solution you have is that if you didn't do this and then you find out you're going to have this problem, is that's when you can teardrop this, and most of the tools have the ability to just auto-add the teardropping in. But again, it's a quick fix. All right, so so going back to this, design these things up front correctly based on contract manufacturer's recommendations. All right, a couple of other quick things here. I know I'm already pushing the hour, but some very quick things. If you're going to create something that you're going to bolt down or you're going to screw in, number one, just make sure you understand that you're putting a lot of force on this here. And if you try to put a screw in here thinking that you're going to make great connectivity to your ground planes, not going to happen. Why? Because you're going to tear this stuff up. And keep in mind over here that one of these planes, because this is a layer right here, if that junction breaks off, you're not going to make connection to it. So don't try to put a screw in here thinking that enough material is going to make connectivity between point A and point B down over here. If you are going to try to make contact with it, make the hole so that the screws or the bolts really aren't ripping apart your plated hole. Most of the connectivity is going to be either on the bolt head or the pan screw head. Okay, and if you are going to put this on, make sure you put a washer up there, because obviously when you turn that screw, especially with a drill, or if you're going to bolt this thing in, you're going to start ripping apart the copper that's on the top. Now, of course, that solution requires another solution. Keep in mind, if you have copper with another material, you're going to get what's called a bimetallic junction. So also make sure you use some type of anti-corrosive chemical because the copper will start reacting with that washer there. All right, finishes. Okay, we're almost there. Guys, hang with me for a few more minutes here. I know I'm a little bit past the hour, but just a few more slides. For layout and for finishes, these boards are going to sit for a while. They're fabricated, but you're not going to assemble them. There's different ways of handling this. One of the things that you can do is you can do what's called a dry nitrogen box. So if you actually have a test floor that has dry nitrogen piped into it, you can purchase a box of this nature, and you can connect it to your dry nitrogen, and you can always keep the boxes purged. And that's one way to do it. We used to do this with wafer sorts all the time. You can also place them in nitrogen bags. And the key thing here is that the room conditions have to be stable. So if you're trying to do this in a garage, it may not work very well. If you have a very controlled environment, it will work just fine. If you don't have that, and you're just keeping these in a manufacturing environment, let's say a shipping room, for example, the copper finishes are going to react with the environment over time. So you basically want to create some level of coverage. One of the methods that's been used traditionally is something called Hassel, hot air solder leveling. So you dip the board in tin lead, and obviously this is an issue now with RoHS, so they have some other type of solution that they're going to do here, and then they're going to blow excessive hot air over that to blow off any excess. The problem with this is that it doesn't work very good for fine pitch leads anymore. Another method that you can use is something called immersion tin. So you just basically stick the tin in a plate, or stick the board in a plating solution of tin. The biggest problem that you have with tin, and this is why they used to add lead to the tin, are the tin whiskers. The lead, for some reason, suppresses the tin, and so that's one of the reasons why a lot of people didn't want to see the lead be removed from the solder, because of the tin whisker issues. They are starting to address this with other solutions. There's also what's called the organic soberbility preservative, and this is a water-based compound, extremely environmentally friendly. One thing I really didn't mention with you is that a lot of the processes that you use in printed circuit board design are pretty, the chemicals are pretty nasty over here, so it's kind of nice to see a process here that's trying to use something that's a little more environmentally friendly. The disadvantage of this, very short life, it's just the 6 months max, so you got to use these boards sooner than later. The most popular one is this one called ENIG, electroless nickel immersion gold. That's why they probably use this term right here, because it's quite a mouthful. Basically what you got is you got gold over nickel. You don't just put gold on top of copper, because the copper and the gold atoms will basically merge with each other. So this is what they do quite often. This is when they start using gold. So they've got these boards sitting for a while, and then they populate them as they need them. I don't know if this really happens as much often now. I mean, maybe for mass manufacturing. However, things change so quickly now. I tend to wonder if they're doing this. Plus, of course, the gold prices are rather high as well. And, of course, one of the big disadvantages, other than just gold prices, is that you can't do rework on these. Okay, very, very quickly with documentation. There's some notes here. If you're going to when you do your notes, do them both in mils and millimeters. Okay, a lot of this equipment is coming from overseas. China's getting involved in that. Europe has their equipment. Canada's got their equipment, right? So people are buying the best equipment from all over the world. Some of it works in mils, some of it works in millimeters. Provide notes and dimensions in both of them, save them the hassle of doing the translations. Footprint libraries, I didn't have any time to talk about this today, but footprint libraries can greatly assist in automating all of your documentation processes. So there's things like courtyards and so on and so forth that you can add to the footprints above and beyond just your copper landing pads that can certainly assist you in automatically creating assembly and fabrication documentation just by you placing them down. Documentation. So there's three major types of manufacturing files: Gerbers, ODD++, 2584. The one thing I'm going to mention about ODD++ and 2584 is that they do contain a net list. And if this is being sent overseas, you're again helping someone possibly reverse engineer things. That's one of the nice advantages of Gerbers. That's why a lot of people like using the Gerbers, is they really are truly dumb files. They just say this is where the copper is located, and that's all you're going to get out of it. So just keep that in mind too. There's two things I want to mention over here. If you can add fab dimensions, that's certainly very useful. But the two things over here is that some vendors do want to have a net list, because then they can verify that your Gerbers are correct. So only provide those if it is a trusted vendor. And the big thing I want to mention here are the backfilled vias. If you're going to use a backfilled via, you have to declare this as a note. What is a backfilled via? I showed you earlier on. I'll flip back to it here so you can see it. Over here, we're using a dog bone in order to break out a large BGA. But now they're not even giving you enough space for even this. So what you can do instead is you can actually tell the assemblers that I'm going to place a via with a hole in it, and then I want you to fill that hole with some material, conductive material, and then I want you to plate over this and smooth it out. So you'll still have the connectivity to all the other layers, but you won't have the solder wick down over here when you place the BGA. So a lot of people don't realize that if you say, well, shoot, I'll put the hole in via, then they don't realize that the BGA, the ball itself, which is solder, will just get sucked right down there and it won't make connectivity. So you've got to actually fill in that hole. So that's what they mean via in pad, but it has to be declared as something that assembly is going to do, and it is, by the way, kind of pricey. So that is my last slide over here. Thank you guys very much for attending. If you have any questions, feel free to contact us here at 9.Connect, and we'll be more than happy to assist.